Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at roots of polynomials. So let's look at trying to solve x squared minus 6x plus 13 equals 0. So we'll be here for a long time if we try and find two numbers that multiply to 13 and add to negative 6. So usually what we've done is use the quadratic formula. So first we calculate the discriminant, so that hasn't changed, it's still b squared minus 4 times a times c. So you get 36 minus 52, which is negative 16. So previously we stopped there and we said that there are no real solutions. But now that we know something about complex numbers, we actually can solve this. We can go ahead and use the quadratic formula. So x will be minus b plus or minus the square root of the discriminant, all divided by 2 times a. So previously we weren't able to go any further because square root of negative 16 has no real solutions. But now we can easily solve this. So negative 6 is just positive 6. On the bottom we have 2. Now root 16 is root negative 1 times the square root of 16. So you know now that the square root of minus 1 we write as I, square root of 16 is 4. So this is 6 plus or minus 4i over 2. So one of the solutions is 6 plus 4i on 2, and the other is 6 minus 4i on 2. Now, because both of these terms have a factor of 2, we can simplify this. 6 divided 2 is 3, 4i divided 2 is 2i, and here we can simplify as well. It's actually 3 minus 2i. So when you have a polynomial like this that has complex roots, they always come in complex conjugate pairs. If z is a root of a polynomial, so too is its complex conjugate. All right, let's now look at a slightly harder question. So we're going to devise a polynomial with real coefficients that has root 2 plus I. Now, because the real and imaginary parts are both rational, a number like this will be the root of a quadratic equation. We're going to come up with such an equation. So note that if 2 plus I is a root, then so too is its complex conjugate. 2 minus I will also be a root. So if you have two roots of a quadratic equation, you can easily find the equation. It's just x minus the first root, which was 2 plus I, multiplied by x minus the second root, which was 2 minus I. So let's just go ahead and expand that. It has to equal 0. So x times x is x squared. Then we multiply the outsides. So I get minus 2 minus I x. Then we multiply the insides. And finally, we multiply the lasts. So because it is a negative times a negative, we put a plus here. It'll be 2 plus I times 2 minus I. So let's just go ahead and simplify. So the x squared term needs no simplification. Now here, when you have like terms, you just add the coefficients. So minus 2 gives me minus 4. So this becomes positive I minus I. That's just 0. So this just becomes minus 4x. Now if I multiply these, I can use the difference of two squares. Square the first, which is 4. Square the second, so I squared is minus 1, and stick a minus between them. So that last term just becomes 5. So x squared minus 4x plus 5 equals 0. So this is a polynomial. It has a solution or a root of 2 plus I and 2 minus I. Let's now look at how complex numbers can help us solve cubics. So let's say I want to solve this cubic here. So I'm going to use the same process we've used. I'm going to try and find a root by trial and error. I'm going to try positive and negative factors of this number here. So you can try a few. We'll see that f of 4 is equal to 0. it is 64 minus 64 plus 16 minus 16. So 4 is clearly a root, and that means that of this polynomial, x minus 4 is a factor. So I'm still going to go ahead and do polynomial long division. So I go leading term into leading term, that's x squared. Whenever I get something up the top, I multiply it by this. So x squared times x squared times negative 4. So now I'm going to calculate the remainder at this step by subtracting. I actually get 0 x squared. I don't stop here though, because there could still be other terms. That means that this remainder, because 0x squared divided by x is obviously 0x, so that's 0, but there could be another number over here. So I'm going to follow the process. I'm going to bring down the 4x, and when I get something up the top, I multiply it by this here. So that will be 0x squared, and of course 0x times minus 4 gives 0x. So now I'm going to subtract to calculate the remainder. 4x minus 0 is 4x. When you get a remainder, divide by leading term. 4x divided by x is positive 4. Now I'll calculate the remainder of the whole thing. So bring down the minus 16. When I get something up the top, I need to times it by these two terms. So 4 times x, 4 times negative 16. Great, I got a remainder of 0, which I should have done because x minus 4 was a factor. So what I've actually found here is that fx, which was my original polynomial, it is equal to x minus 4 times x squared plus 4. So before we did complex numbers, we couldn't solve for that equaling 0. So if x squared plus 4 equals 0, you can go x squared equals minus 4, and so x will be positive or negative 2i. Make sure you get both solutions here. So our solutions, we have 2i, negative 2i, and we already had the solution 4. So these are the three roots of the polynomial. So the fundamental theorem of algebra tells us that if you have a polynomial of degree n, there are exactly n roots. Sometimes you have double roots that you have to count twice, or triple roots that you have 3 times. But there are always n roots. So before we did complex numbers, we could find them all. We didn't know how to find all 3 roots of a cubic, but now that we know complex numbers, we can always find 3 roots to a cubic, 2 roots of a quadratic, 4 roots of a quartic, and so on. Sometimes you'll get 2 roots that are the same, but now we can fully utilize the fundamental theorem of algebra. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.